Sometimes we're given a composition in mass percent, weight percent, and we want to know mole percent instead. So here we have a 60 weight percent benzene and 40 weight percent toluene mixture. How to calculate the molar percent? Well, if you have weight percent, choose a weight basis. And so I'm going to choose 100 kilograms, just a nice even number. If I was given a mole percent, then I would choose a molar basis, like 100 moles. Now the trick is to calculate how many moles of benzene are in this mixture, 100 kilograms of this mixture. So we write 60 kilograms of benzene is in the mixture, and divide that by the molecular weight, which is 78 kilograms of benzene per kilomole. And this equals 0.769 kilomoles of benzene. We do the same thing for the toluene. 40 kilograms of toluene divided by its molecular weight, 92 kilograms of toluene per kilomole of toluene. I guess I should have specified kilomoles of benzene up here. This is equal to 0.435 kilomoles of toluene. So these are the numbers of moles, kilomoles of benzene toluene in this 100 kilograms. So now I can add these together to get the total number of kilomoles present, which is 1.20 kilomoles total. So now if I just take my kilomoles of benzene divided by the total, I get the molar percent. So we get mole percent here. It gives me the mole fraction, but I have 0.769 kilomoles of benzene divided by the total number of moles, and that will give me 64.1%. The ratio is 0.641, so that's 64.1%. And likewise for the toluene, I can calculate it, or it's just 100 minus this, 35.9 mole percent toluene. So that's the toluene, this is the benzene. So in the previous part, we found that 100 kilograms gave us 1.2 kilomoles. Our actual flow rate was only 10 kilograms. So what we have is 0.12 kilomoles. And this is all per second. So to get the flow rate in moles per second, so I'll write this per second. To get the flow rate in moles per second, N would be equal to 0.12, I guess I'll give it three significant figures, kilomoles per second. But the problem specifically asks for moles per second. So we'll put 1,000 moles per kilomole. Kilomoles cancels, of course, and we're left with 120 moles per second. To calculate the volumetric flow rate, we'll have to use our molar flow rate, our mass flow rates again, because we have the densities. They're given. So if we want to know the volumetric flow rate of the benzene, we write its mass flow rate, which would be 6.0 kilograms of benzene per second, and divide by the density, which was 0.9 kilograms per liter. Actually, it was given in grams per mil, but that's the same as kilograms per liter. And then we convert the liters to cubic meters because the problem specifically says cubic meters per second. So we have 1,000 liters per cubic meter. So liters cancels and kilograms cancel, and I'm left with cubic meters per second. And this was 6.67 times 10 to the minus 3 cubic meters per second. We do the same thing with the toluene. We had 4 kilograms of toluene per second. And its density was given as 0.8 kilograms per liter. And we convert the liters to cubic meters. And we get 5.00 times 10 to the minus third cubic meters per second. Now, if I assume these volumes are additive, meaning that 10 liters of benzene plus 10 liters of toluene gives me 20 liters, then all I have to do is add these together, and I will get 1.17 times 10 to the minus second cubic meters per second. And that's my volumetric flow rate. Oftentimes we need the linear velocity, for instance, in the calculation of the Reynolds number. So we just take our volumetric velocity, or flow rate, and divide it by the cross-sectional area of the pipe. So we have 1.17 times 10 to the minus 2, that would be cubic meters per second, and we divide by the cross-sectional area. So the diameter of the pipe was 10 centimeters. That's the inner diameter, that's what we want. And I can either use pi r squared or pi d squared over 4. Since it's so easy to divide 10 by 2, I'll just use the radius then. So pi times the radius squared, which is 5 centimeters. So it's squared. And then we need to convert the square centimeters to cubic meters. And so we've got 100 squared centimeters squared per meter squared. And let's see, the centimeters squared cancel, and 2 of the meters squared cancels with the meters cubed up here, leaving just meters per second. And so the answer then is about 1.49 meters per second.